Okay, so welcome everyone to my talk, and I will be discussing light-matter interaction at the level of single particles. So what happens when single photons interact with single particles of matter that are single atoms or single molecules. And a goal of my talk will be to demonstrate that complexity and the concepts of complexity play a role also in such a simple paradigmatic system. So this archetypical system has been at the heart of quantum mechanics since the early beginning, right? And you can think about photoelectric effect and even experiment leading to Nobel Prizes such as the one by Serge Haroche implied the manipulation of this interaction at the single particle level. Now, in the future that we are imagining, this interaction will allow us to interconnect multiple and diverse systems that can be tailored for different applications, from quantum sensing, computing, communication, or foundational experiment. And at the heart, you always have a system which should be capable of storing, processing, or sensing information based on the manipulation of internal degrees of freedom. And the same system should be ready at some point to transfer this information coherently into some non-classical state of light that will then propagate to the next one to interconnect these two systems. So this is already setting some important requirements. We would like this interaction to be coherent, such that the information can be reliably read, written and read from the quantum emitter to the state of light. And these quantum emitters platforms should be scalable. We should be able to produce them massively, and it should be possible to interact with each other, okay? We are facing actually in this, with respect to this challenge, important problems with conventional systems. On the one hand, we have atoms and ions in the gas phase that are characterized by a highly coherent kind of interaction, but at the same time, this typically happens in free space and it is therefore quite weak. Moreover, complex experimental setups makes it hard to scale up the number of isolated quantum systems. On the other hand, we here well know that it is possible to nanostructure the environment in the solid state around defects, for instance, in semiconductor materials, in order to enhance light-matter interaction. But this comes at the cost of the coherence due to the coupling with the reservoir in the solid state and inhomogeneity, meaning that in the solid state, each quantum emitter is typically different from one another, and therefore it is hard to have them interacting. And this is why it is important to study different platforms, such as the one that we are investigating in Florence, which is based on organic molecules in the solid state. So my goal is to demonstrate that by bringing together traditionally distant fields of molecular chemistry and nanophotonics, we can attain at the same time scalability and coherent control. Now, why scalability? Well, molecules, just like atoms, are all identical by nature. They have some specific features, and that is that we can engineer the emitter properties, guided even by ab initio calculations, on very different energy scales, from the tens of gigahertz of spin degrees of freedom to tens of terahertz of the nuclear vibrations, up to the optical excitations of electronic transitions. Okay, so we change the constituting atoms and then we can engineer the spectrum over very different energy scales. It is also possible, and if you want to know some more, here is a possible reference, to deposit molecules on nanostructures and therefore control interaction and dissipation by playing the game of the density of states. We have heard, for instance, from Paloma yesterday, Purcell enhancement and so on and so forth. So we can tailor the density of states and therefore minimize, for instance, the dissipations and the coherence rate due to the coupling with the reservoir of optical or mechanical degrees of freedom. Now, in my talk, then, you will hear the first steps that we have been taking towards the realization of interfaces between, so this interconnect that you were seeing in my first slides, between single photons emitted by the molecule, so the quantum state of light, and single phonon, for instance, so single excitation of nuclear motion. We also have some work about spin-photon interfaces in molecule, okay? And this is, if you wish, a first aspect of complexity. The fact that molecules have very different ways to interact with the environment. This brings about a term of complexity. At the same time, in the second part of the talk, or in the first part of the talk actually, I will show you how we can increase the number of molecules in our system and how we can let them interact with each other. Okay, so interfaces and scaling up the number of molecules. This is my goal. How do we do that? Okay, so this is more or less the workflow. We start by depositing molecules from solutions. You'll see these are special molecules, and actually a combination of a guest molecule in a host matrix on chips that can be functionalized for different applications, from sensing to communication and even computing. And the basic principle is quite simple. So to first approximation, we can describe our molecule as a two-level system. This is nothing but a high-quality factor oscillator whose properties, both in the dissipation rate and in the transition frequency, depend on the local environment around the molecule itself. So we can use the molecule as a transducer to optically read out properties such as temperature or the presence of a local charge, because this will change the oscillator properties. And the sensitivity of this mechanism is given by the fact that it is a very high quality factor oscillator. The spatial resolution given instead by the sub-nanometer scale of the molecule size itself. Okay? So we have a very nice nanoscale sensor. Now, the possibility instead to address one molecule at a time provide us a tool to design exquisite non-classical sources of light. And in particular, if we use a trigger laser to excite the excited state of a highly radiative transition, after spontaneous emission, we are left with a train of pulses containing one and only one photon per pulse. Okay? This is how a single photon Fock state is defined, actually. And this is an important resource in quantum technologies, from communication to, for instance, linear optical quantum computing. And depending on the application, you have to set different requirements on the emitted photons. Now, I'd like to introduce to you also the concept of two-photon interference. Maybe not all of you are familiar with that, but this is actually the only way that photons have to interact with one another at the level, let's say, of single photons, as nonlinearities are so weak at the single photon level. Okay? And indeed, like all protocols relying on, let's say, for linear optical quantum computing, for instance, rely on the concept of two-photon interference. The idea is as follows. Imagine you have two photons, two indistinguishable photons impinging on a beam splitter. Now, classically, we have four possible outcomes of this problem, both photons being transmitted, both being reflected, or one is transmitted and the other one is reflected. Now, what happens, because photons are bosons, is that we have to compute the interference of these two probability amplitudes, and this interference ends up being destructive. So, as a matter of fact, photons coalesce at the output port of a beam splitter. They always want to leave it from the same output port. Okay? And so you can think about this as an effective photon-photon interaction, the presence of one photon conditioning the transmission properties of this beam splitter for the other one. Okay? Now, what I said is that these photons have to be indistinguishable, so they have to be exactly in the same quantum state. And this is not trivial to obtain, especially in the solid state, requiring lifetime limited transitions. Now, I was showing this two-level atom as an approximation, but in the solid state, these two levels coupled with, for instance, with a phonon environment, and therefore this broadens the transition line due to the phasing, due to scattering with phonons, and typically the line width of this transition is not just 1 over the excited state lifetime. There's some dephasing term. And if this dephasing terms broadens the line, then you lose this feature of indistinguishability, and in turn, you do not get to photon interference. Okay, so for most application in linear optical quantum computing, and also for many protocols in quantum communication, you have to have indistinguishable photons and lifetime limited transition. And in practice, this means that many experiments in my lab are done at low temperature. Low temperature meaning around 3 Kelvin or 1.4 Kelvin. Okay. Yeah, here, this is just to say that actually, besides realizing excellent single photon sources with isolated quantum emitters, if you push light-matter interaction to the strong coupling regime, a single quantum emitters can also be used as a nonlinear element at the single photon level. Okay? Which molecules are we talking about? Well, we are using mostly polyaromatic hydrocarbons. These are molecules made out of carbon atoms arranged in a honeycomb lattice and hydrogen terminated. They happen to be the largest molecules to be found in the interstellar medium, okay? And this is, for instance, spectroscopic data taken from the Hubble telescope showing absorption from ionized PAH, okay? But the molecules that we use, dibenzoterylene, we just buy it commercially. We do not just use the molecule in itself, we embed this molecule with very simple method under a chemistry hood in a matrix, in a crystalline matrix. And now what is the role of the matrix? The first thing is to shield oxygen diffusion. So with respect to the other fluorophores that we have seen in these days, we're talking about single molecules that we investigate for months. The very same molecule, I even give it a name sometime. This is whatever, Pietro, Maya, Costanza, because, you know, like you have to save data, no? And so you have to say, like, this is molecule X. So the same molecule lasts for months inside a cryostat. And then the fact that this is a crystalline matrix means that the molecule sits always in the same environment, and therefore it always has the same transition frequency, apart from very small fluctuations, okay? Because the atoms around it, the electrons around it are always at the same distance, more or less. Okay, another point I'd like to make is that we can control to a certain extent, statistically, the average number of molecules per nanocrystal. We can do single molecule studies, but we can also dope the crystals with a lot of molecules. And this is interesting, for instance, to study cooperative effects, superradiance and subradiance and things like that. Many things that we can do. And we're also trying to use such cooperative effects to realize multiphoton quantum states, so more complex states of light. What I also wanted to say is that because we start from such, we can grow crystals of different size, and it might be worthy mentioning here the fact that we can deposit these nanocrystals wherever we want. We can even, for instance, embed them in a turbid medium, in a complex medium, and that, I think, would be very nice to study speckle pattern and more complex things from single quantum emitters or 2 quantum emitters embedded in turbid material. Now, the outline of my talk today, however, doesn't contain yet results of this kind. I'll be showing how to realize molecular single photon sources and how we can characterize them in terms of the most important figures of merit for single photon sources, that are the purity, so the probability really of getting only 1 photon per pulse with respect to getting many photons within the same pulse, the interference ability, so how good and how indistinguishable these photons are, and the brightness. I will then focus on some special dishes, which are indeed the scalability, the possibility to have to interfere photons from distinct molecules, and how far can we go in the number of molecules. And finally, I will show you some application in sensing. Okay, so how do we produce the single photon sources? As I said, we start from a situation in which we have on average 1 molecule per nanocrystal, And then we exploit phonon-assisted excitation in order to detect the red-shifted fluorescence. Now, if you look at the spectrum of fluorescence at low temperature, just at low temperature, talking about the coherence of single emitters. I mean, this is how narrow the transition is at low temperature, so it is only 40 megahertz, whereas at room temperature, this becomes 50 nanometer, okay? So speckled patterns would be quite different. And what you can also appreciate is that more than 50% of the emission is actually in this zero phonon line, which implies no phonon exchange with the internal vibration of the matrix itself. So this is the only one which is really potentially Fourier limited. And so we perform excitation spectroscopy in order really to check the line width, and we obtain typically 40 megahertz line width that is really lifetime limited. Another important detail is that of spectral stability. If we repeat excitation spectroscopy over time, you see that the transition frequency is always stable at the same point. Okay? This is actually important for many applications. What about the purity? This is accounted for by measuring the second-order autocorrelation function in the intensity, and its value under zero time delay is like an upper bound for the purity. As I said, the probability of getting just one photon per pulse. Experimentally, this is done with the Hamburg-Brown twist experiment. So essentially, we split the photon stream from a single molecule in two, and then we calculate the coincidence probability as from this two output port of the beam splitter as a function of the relative time delay. And what we have is that this huge suppression by 99.5% of the multiphoton probability at zero time delay. Okay. This means that it is essentially impossible to get two photons at once from a single pulse. So the purity is extremely high for these single photon sources. This is an example, I mean, as you can see, obtained under pulsed excitation. There are several works aiming at optimizing collection efficiency, and it has been demonstrated, for instance, in the group of Vahid Sandogdar, that at room temperature, by structuring simple multi-layer geometries, we can attain near unity collection efficiency. Now, other feature. This is another example of anti-bunching, so the second-order autocorrelation function showing sub-Poissonian statistics, this time under CW excitation. Okay, so you see this again, this suppression. Photostability, not just the molecules last forever, but if you look, there's no blinking. So the fluorescence, there's no intermittence in the fluorescence that you probably have seen and you're familiar with if you're using colloidal quantum dots, for instance. You see that fluorescence is always stable, and the molecules are also quite bright as we get at saturation on average 2 million count per second. Spectral diffusion I already mentioned. What about indistinguishability? Now let me show you some experiments done in our group. So the first thing, to measure indistinguishability, you actually make it a bit simpler. Instead of having two sources here at the input port of the beam splitter, you just split the single photon from one molecule on the two arms of the beam splitter. And this is done here. Experiments are done at low temperature, and here you see that actually there's no particular non-photonic engineering. There's just a gold layer underneath, and the molecule is placed at the right distance such that you get some constructive interference in the in this direction, in the observer direction, but very little engineering here. Then we use this notch filter in order just to detect the zero phonon line, which is the one delivering potentially indistinguishable photons. And then we split these in two arms that we combine in this beam splitter, which is called, let's say, the Hongu-Mandel configuration. We also have a fiber polarization controller in order to switch between the distinguishable and the indistinguishable case on purpose, okay? At some point we make artificially these two arms distinguishable in polarization in order to estimate a visibility figure. And you see indeed that when the two photons are orthogonal, this is the feature that we get, the G2 function again. This is what it's measured here. And instead, for parallel polarization, we get again this strong suppression that corresponds to the coalescence of photon with a visibility of above 97%. Okay? So indeed, we're dealing with indistinguishable photons from one single emitter. So far, so good. But the dream is really to scale up and be able, for instance, to address a situation like this one. So we have an optical network where single photons are pumped inside the network, each of them emitted by a single molecule. Okay? So this, at the moment, this kind of experiment is not possible. What people do to demonstrate, for instance, boson sampling and so on, is to take one quantum emitter and do temporal demultiplexing. Okay? So you take just one and then you feed with some delay line the single photon just from one quantum dot to each waveguide. But then, of course, you are losing a lot in terms of coincidence rate. So this is really, and this is a problem. I mean, what you need many photons in order to benefit from any quantum advantage. One photon is not enough. But you are immediately losing if you're just using the multiplexing. So it's really, would be really a big milestone if this experiment would become possible. That's what we are trying to do. The first challenge is to deal with the residual inhomogeneity. So I said molecule lives in a crystalline environment. It's rather happy. However, you can have slightly different modification of the local environment yielding inhomogeneous broadening, which is visible, for instance, if looking at this excitation spectroscopy. So here what we are doing, we are looking at the redshifted fluorescence as a function of the excitation laser frequency. So this is now a large crystal, and you see that these dots, they correspond to single molecules that lights up in different moments of this video because they are resonant at different transition frequencies. Okay? So what is the consequence? The consequence is that if you go to do two-photon interference between this molecule and this molecule, you would have zero visibility. Okay? So we need to find a way to compensate for that. The first traditional way is to use Stark shift. You apply an electric field with some electrodes to our molecular crystal, and this will shift by a different amount the ground state and the excited state, and therefore will result in a net shift of the transition frequency. Now, because our molecule is inversion symmetric, we can neglect the linear term, and we only have a quadratic dependence of the transition frequency as a function of the applied voltage. Now, in this experiment, we wanted to be a bit fancy, and so we used 2D materials as transparent electrodes. There are some advantages, but there's no need. And you can see, indeed, this quadratic behavior, and you can also appreciate the fact that we could scan through hundreds of gigahertz, which is the entire inhomogeneous broadening. This means that I can bring molecule X in resonance with molecule Y. What is the problem of this method? The problem is spatial resolution. So it is very hard to say, let's say, to apply a different field to molecule here and molecule here to control it. So do we have any alternative to that? We recently discovered that we could essentially locally induce a field by shining another laser that ionize charges that are trapped in our molecular crystals for a long time because we are at cryogenic temperatures. Long time means hours and hours. And by controlling the doses deposited by this external laser, we can control the frequency shift, as we were doing with our electrodes, but this time on the spatial domain given by our laser spot. Okay? So that might seem quite crazy, and indeed we tried this crazy experiment of tuning molecules sitting in different nanocrystals one after the other, trying to bring them all to the same transition frequency, potentially then doing two-photon interference from distinct molecules. So how far did we go? Okay, so that was the initial situation. We have these 5 emitters that are about 20 microns apart and 20 gigahertz away in frequency, as you can see from this excitation spectrum. Now, with the same kind of animation, you see that they appear in different moments. After our curing protocol, now here the mouse is not working. Too bad. Okay, you have to actually, you cannot see this in the animation, but you can appreciate it here. After our tuning protocol, we end up with this situation in which all molecules are within twice their line width. So we have 5 emitters that used to be 20 years apart and now are really resonant close by, but they are also now resonant all to the same transition frequency. So we're kind of getting close to this idea of getting indistinguishable photons from multiple quantum emitters, going in the direction also of quantum advantage. Is this enough to get indistinguishable photons? We had to prove it. So in this experiment, we then collected the emission from single photon emission from distinct sources, and we recombined them at the usual fiber beam splitter, looking for coalescence. But this time we have 2 distinct sources. Do not split single photons from the same one anymore. And of course, we had to apply our routine for shifting, so with multiple shifting pulses in order to get these 2 molecules now to the same transition frequency. And this is the result. Again, you have the suppression of the coincidence probability, which is an evidence for coalescence of photons. This time with a slightly lower visibility, if you integrate over the entire pulse duration. Of course, if you just look at the very pixel of tau equals 0, then you get a very high visibility. But if you integrate over the entire pulse area, then you get 40% visibility. And this is due to some residual spectral fluctuation that we are working on it. Still, it is actually very good data, okay? Especially if you consider that there's no cavity that typically is used in order to improve the visibility, and there's no charge depletion scheme that suppress charge noise and therefore spectral fluctuations. I mean, these are a bit technical details. If you want, I can speculate more to explain this. Okay. Now, the other point I want to make is that in order to attain scalable platform, we also have to show the possibility to integrate molecules on waveguides or on cavities. Okay, if what I've shown up to now was state of the art, let's say molecules are behaving very well compared to the existing quantum emitters, with respect to the integration, we are lacking a bit behind. So we have to work hard in this direction. Although there has been some work in which we have shown, for instance, evanescent coupling of molecules to silicon nitride waveguide, like even hybrid plasmonic waveguides. But because they are not embedded in a semiconductor, essentially, and which brings advantages because I can fabricate hybrid geometries and bring them close to graphene or to many different material platform. At the same time, there's no natural platform that we can nanostructure easily. So the path that we are, okay, so this is another example in which, for instance, an open Fabry-Perot cavity was used, and actually strong coupling was demonstrated at the level of single molecule. Okay, so I mean, this is another example for the evanescent coupling of single molecules to waveguides. The path that we are recently following is that of direct laser writing. So it is possible to disperse our nanocrystal into a polymer photoresist, for instance, and then use direct laser writing to induce 2-photon polymerization around a selected quantum emitter and fabricate very complicated, even 3-dimensional structures. In this case, for instance, we have demonstrated the coupling of molecules to suspended waveguides or to microlenses such as this one. And what we have also shown is that after this fabrication process and the development with solvents and everything, the nice properties of the molecule are preserved. So we still get very nice anti-bunching and high single photon purity. lifetime limited emission, and photostability, even in the emission from molecule embedded inside such a microlens. Okay, so we can use direct laser writing, and we're now trying to fabricate microcavities in this way. From this first experiment, what we have also demonstrated that for molecules inside the microdome, we effectively get 40% collection efficiency at the first lens, which corresponds to an enhancement of a factor 12 with respect to the molecules sitting on a pristine covered glass. Okay, and that the emission pattern is particularly suitable for coupling to single mode fibers with 50% efficiency. This might seem for you all details, but it is very important from a technological point of view to get. If you want really to maintain appropriate single photon statistics, but you lose 90% of the photons, then you easily end up with the same Poissonian statistics as before. So these numbers are actually quite relevant. And as I was saying, we're now trying to develop cavities with these techniques. Now, let me, how am I doing with time? It's greenish, reddish, okay. Okay, I still have half an hour. Ah, okay, then I can relax. Okay. Do you have questions from this first part before I move? Yeah.
The laser induced detuning, is it because of ionization?
Yeah.
And how do you control how much detuning? Is the laser power or?
It's the doses. So, I mean, I can either change the laser power or the illumination time. Okay. What is true is that it's not something that I know a priori. So it's not that I can, let's say, I do it in one shot. If you have observed, I have to check after each sequence how much has the molecule moved, and then I repeat it, and then I repeat it. Now what we are doing is we are combining the traditional electrode shift with the laser in order to get a better handle on this. So there is another important aspect about this tuning that maybe I will just mention here on the whiteboard. And you remember I was talking about residual spectral diffusion. Is there a way to erase? No. Okay, because I cannot move from here because there's a recording in progress. Okay, I mean, essentially because we have this quadratic dependence of the molecule transition frequency with the applied voltage, now what happens typically, and this is true for many quantum emitters, is that you want to bring, for instance, molecule 1, which is this one, to this target frequency, which is the frequency for emission of molecule 2. And now what happens is that you observe enhanced spectral diffusion. Now, why is that? The reason is, we believe, and we have demonstrated, and I even have slides about that, that spectral diffusion is related to charge noise in the material. So the thing is that the same charge noise here and here, because of the different gradient in this polarizability tensor, results in very different amplitude of the frequency fluctuation. Okay? So this is another point that we are now addressing. Because the molecule has a polarizability tensor which is highly anisotropic, we're now trying to move the frequency following this polarizability tensor along a line which is, if you wish, more flat in a sense, and in such a way to attain the same transition frequency with a lower gradient. Okay, so this is
Going the other way around, if you want to probe this charge fluctuations.
That's always a compromise. That depends very much on what you want to do. And indeed, for instance, and this has to do with the flexibility and the tunability of this molecular platform. For instance, if you want to detect a single electron, the charge of a single electron, then what you want is to have these as steep as possible. And actually, more than that, you would like actually to have a situation where the symmetry is broken and to have a linear Stark shift. Okay, so this we have also demonstrated. And what you can do, instead of changing the molecule, you can also just change the matrix around it. If you change the matrix in such a way that after all you break the transition symmetry, then you can get linear Stark shift and enhanced sensitivity to charge fluctuation. But then if your target is a single photon emission and stable transition frequency, then this is really not what you want. Other questions? Okay. So harvesting the coupling with phonons. What I was mentioning up to now is the fact that phonons are just a source of decoherence for us. They broaden the transition line. Now what we're trying to do is instead to better understand this interaction and to even harvest it. Okay, so the first experiment we did is the following. So we deposited our molecular crystal on a suspended membrane, and we use the molecule as a sensor. So in this case, we have calibrated by changing the cryostat temperature, the broadening of the line as a function of the temperature, and then used it to map the temperature on a very complicated membrane such as this one. In this experiment, we were using a heating laser as a source to inducing silicon absorption in a certain point, and then measuring the temperature using our molecule as a transducer as a function of the relative distance between our heat source and the molecule. And you can see that these are the results that we tried to fit with the heat diffusion equation, whereby we had to introduce the quadratic dependence of the thermal conductance on temperature in order to nicely fit our experimental data. So the message here is that molecule can be used as an excellent temperature sensor in a temperature range where there is no real alternative, which is a little invasive. This requires no further structuring. We do not have to put electrodes on top of our membrane, and the sensitivity is down to 0.01 Kelvin. This is an interesting temperature regime because in this temperature range, the dominant phonons are long wavelength, they have long mean free path, and therefore one can envisage coherent scattering effects beyond the diffusive transport. So we are now studying kind of a hydrodynamic heat transport regime using the molecule as a sensor. Okay, now with that, I think I already shown to you the possibility of using molecule as single photon sources and how we can scale up the number of quantum emitters, and also the possibility of using molecule as sensors. Now, because I have more time, and I didn't expect it, I'll show you something else. Not this. I wanted to show you something else. Just give me 1 second. This doesn't work. I wanted to show you how we can go beyond just coupling with phonons, and how we can use the molecule as a cavity optomechanical platform, because this resonates with some discussion I had yesterday. Sorry, I don't have this. I mean, I will just talk. So the idea is that the molecule couple with internal vibrations, okay? So because in the excited state you have a different electronic configuration, the nuclei are excited, and therefore you have this Stokes shifted emission, okay? Raman transition, if you wish. And this is a form of optomechanical coupling. Now, if you write the Hamiltonian of this system, this is exactly equivalent to a cavity optomechanical system. But it's a very special cavity optomechanical system. And why? The first thing is that, where's the cavity? The cavity is given by the optical transition itself. Optical transition, which has an amazingly high quality factor. Right? It's 40 megahertz at hundreds of terahertz of the transition frequency. And what is the mechanical resonator? The mechanical resonator is the smallest one you can think of. Two atoms moving, one with respect to each other. And the consequence is that the mechanical frequency is in the tens of terahertz regime. And this has to be compared with typically at most some gigahertz of mechanical oscillators. Therefore, one of the important message is that the mechanical resonator will always be in its ground state. So we can explore actually a cavity optomechanical regime which is impossible to do with traditional optomechanics. There's one problem, and the problem is the dissipation rate of the mechanical resonator, okay, which is typically in the picosecond time scale. So what we are now trying to develop are methods to to compensate for this rapid relaxation rate. And we're doing this in two ways. Either you deposit our molecule, as I was showing, on a phononic crystal membrane, and in this case you avoid, you essentially get long-lived phonons the same way you would get inhibition of spontaneous emission. And so in this way, we try to get metastable state, metastable vibrational state, to go beyond just this two-level system approximation. And the second approach and strategy that we are following is to essentially use very high optical power in order to essentially prevent the vibrational state to decay, because the optical transition is simply more probable than the vibrational relaxation rate. So these are the two paths that we are following, and one of the application of this of this vision is the following. So if you have this vibrational level of the molecule, which is actually it's 5 terahertz in particular, 5 terahertz away from the ground state, what we can do is to shine a quantum cascade terahertz laser here, because we can deposit the molecule directly even on top of our terahertz laser due to this portability. We also shine now a very intense, in order to make sure that this guy doesn't decay fast enough, what we call a Stokes laser, okay, that matches then the ZPL frequency and then detect photons at the ZPL transition frequency. So we can use the molecule in this case as a terahertz up converter, exploiting in this case really this complex nature of the molecule and the interface between phonons or vibrations in this case and optical excitations. Okay, so this is ongoing work. We have a theoretical paper which is published on this subject, but the experiment is still kind of challenging. And one of the challenges, there are technical challenges, and these I believe we have solved. There's another thing that we have to work on, and this is the fact that if you want this effect, you need to have that this transition is both Raman active and infrared active, okay, which requires breaking of the symmetry of the molecule. And this is another reason why we need to have some engineering. And so now we are working on this engineering of the matrix in order to get symmetry breaking and therefore get this transition, which is both Raman and infrared active at the same time. Okay, yeah. No, but I wanted to say just one thing. I wanted to, because, I have time. Basta. I wanted to, one second, because then the thing doesn't work anymore. I wanted also to thank Bart van Tiegelen from my side, because I used to work on light scattering complex media, and Bart taught me a lot about this. And actually, I even have, I want to remember him with these pictures that I took back during a conference in Jackson Hole, in which I remember Bart really having a lot of love for life besides physics. So me dancing with Bart van Tiegelen is there. And after all, I want to thank all my collaborators in Florence, abroad, and funding agency. You for the attention.